Okay, we're almost at the end. Is that not exciting? We're almost at the end. So, chapter 12 is a really important topic called constrained optimization. If you're wondering why we just don't have the math department teach some math class, there's a variety of reasons, but one is what we do in chapter 12 and chapter 13. The math department really doesn't even teach to undergrads. They don't consider those techniques that they deal with very often. So when we actually put this course in, the math department said, "Oh, we oppose that." And then we sat them down in a meeting with other people there and said, "Do you guys teach this?" "Well, no." "Do you teach that?" "Well, no." "Do you teach that?" No. And so we ended up being able to teach this class because we showed that the math department doesn't teach this stuff. And one of the things that the math department doesn't teach is constrained optimization. Basically, 12 and 13, the whole of chapter 12 and 13, they teach to graduate students, but they don't really, it's not really part of their undergraduate experience. Good? All right, so very quickly, I want to talk about this guy. And Cournot and Bertrand, Duopoly. They developed theories about what we call duopoly. Duopoly is when there's two, right? Not a monopoly where there's one, not an oligopoly where there's a few, but when there's two, okay? And it turns out that two is more than a tad unstable. But let's chat here, okay? So let's just say, and this is game theory, right? We're doing a little game theory, very little game theory. But the math we've learned, the math we've learned, and the math we're about to learn is all good parts of game theory. And if we had more time, and I'm assuming when you go on and take your next more advanced courses, now that you've had the math, they will you'll get game theory with this the calc built in. But anyway, so we have a market, right? We have, right? That's a demand curve, yes? But we only have two businesses. So we could write this out where Q1 is the quantity of business 1 sells and Q2 is the quantity of the business 2 sells. Okay? Now, the problem with all of this, of course, is that this is essentially a competitive model. What we're doing is we're figuring out what the competitive outcome of this would be. When in fact, these guys both have kind of an absolute ability to set price, right? And we'll get back to that, but let's also assume that the two of them have the same cost, and therefore the total cost of this whole thing is some, constant K plus C times Q, right? And that in QI. So that would be I equals business 1 or business 2. All right? Exciting? Okay. So that means the profit of firm I would be P times QI minus C times QI minus K. Okay? No? Yeah. 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 P times Q, right? So this is total revenue, and that's total cost. Profit equals revenue minus cost. Then we can take and substitute for the P in our equation with the demand curve, right? So that means the profit of firm I is A minus BQ1 minus BQ2, all of that times Q1 minus CQI minus k. Okay? So 1 and 2. And basically, the profit for, that's firm 1, not I. Okay? And the profit for firm 2 is this same equation, except that's a Q2, not a Q1, right? So the profit of firm 2 is A minus B Q1 minus B Q2 times Q2 minus C Q2, and that's a 1. But those things are the same, right? We're assuming those things are the same. Now we differentiate these all and do a little math, and we get what are called response functions. Okay? And you can do this math. It's not important that we do it, but Q1 is A minus C over 2B minus Q2 over 2. And Q2 equals A minus C over 2B minus Q1 over Q2. Now we can do some substituting and playing, okay? And if we do that, or we can use Cramer's rule, we get the following, right? Q1 equals Q2 equals A minus C over 3B. That's a reduced form equation. Why? Because that's all parameters, right? We've talked about this before. There's nothing there but parameters. So what is this telling us? He said wonderingly. What is this telling us? Well, the answer is simple. It's telling us that the way for them to maximize their total profit of the two of them, what we would call the joint profit, is for them to split the market 50-50. Okay? That's what they should do. So if we do the optimizing calculus problem, the answer comes back, oh, you should split the market 50-50. But the problem with that is that each one can gain a little at the other's expense if it doesn't follow that rule. So we could figure out we could take this reduced form equation, right? Figure out what Q1 and Q2 are, then go back to the other equations, figure out what the price should be. Okay? But this is a duopoly. They don't have to charge the same price. In a competitive world, this solution here, in a competitive world, that solution here would just happen. Right? If you had a competitive market, the solution that you calculate out would just happen. But it's not going to happen here. And the two are going to respond back to each other, okay? And they're going to fight with each other. And they're going to drive the price down. And in fact, they're both going to lose money in the end. And it's this whole game theory of how we take that next step, okay? So what I'm trying to do here is not teach you any game theory. What I'm trying to do is show you that a simple maximization problem, this simple maximization problem can come up with the best answer, but it's not necessarily, and best being but come up with what should be the best answer, but it's not necessarily the answer that's going to result. These guys are in a prisoner's dilemma. Hopefully you all know what a prisoner's dilemma is. Duopoly is a classic prisoner's dilemma. How can they resolve this problem? How can they resolve this problem and end up here? Well, they have to collude. They have to work together. Okay? So there's a whole story we can tell, but that story in this case is, why isn't the outcome in this market the profit maximizing outcome? Why isn't the outcome that's best for both firms? Okay? So sometimes we do the math, and then we realize in the real world that that's not what happens, and then the story we tell is why the optimal outcome, the mathy outcome, is different from the real world outcome. And that's a lot of what game theory is about. Why is the behavior of an oligopoly different than the behavior of a competitive firm? Okay? So again, all I'm trying to do here is say, hey, we may see these situations where the correct answer isn't, or the answer that happens isn't the one that we get from, okay? Let me give you another little example. Let's suppose this is our function. Okay, here's x, here's y. Here's our function. If I do the calculus on this, where am I going to end up? Well, I'm going to end up right there at point A. A is a minimum. What if what I want is a maximum out of this? Well, the maximum is all the way out at infinity, and that, my friends, is a problem. Okay? Let's suppose that I'm doing utility. I'm looking at consumer utility, yes? That's an S. And so I'm saying, look, my utility is a function of two goods that I buy, X and Y. Well, if I only look at that, all that the math is going to tell me is if I don't have stuff, my utility is low, and if I have lots of stuff, my utility is high. And the more stuff I get, the higher my utility is. So basically, this is going to tell me nothing that I didn't already know. There's no interesting story to tell here. Okay? So what we're going to do in these cases, we've already sort of done this, we just didn't tell you. We did it a simpler way. But what we're going to do in this case is draw a line on this graph like that. And we're going to call that line a constraint, a limit. We're going to say, look, we need to maximize our utility, but we only make, $100. We only make $100,000. We need to maximize our utility, but our income is going to constrain us, how much of X and Y we can buy. Now, if I do the math, I'm going to get point A and this point over here, let's call this point B. I should get point A and point B showing up in the math. I'll get probably 2 points, and it'll be A and B, or I might get A and B. But it's possible now that A and B are maximums. Certainly it's likely that if we do the math, B is going to turn out to be the maximum point, the highest I can get. Okay, is everybody excited by that? So hopefully you've done these things before. You just didn't know what you were doing. And by that I mean you took 302. You were supposed to take 302 before you took this class. And probably in 302 you did indifference curves and budget lines. And maybe you did isoquants and isocost lines. Yeah? Well, those are calculus problems. Those are maximization problems with a constraint. All right? And that's what chapter 12 is about. Finding that best point if I limit a range of the function. Okay? So if this constraint is here, the only place my correct answer can be is somewhere in there. I have constrained the range of the possible answers to this problem. And so I'm not picking the global max. I'm picking the max or the min in this local range there. Okay? And you're thinking, yeah, this is going to be fun. Okay? 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 So let's just think a problem we've already done. And I'm going to expand this kind of two different ways just for no good reason. Okay? And let's say that our total cost, the way we've written out before, we just made it a function of quantity. But let's say our total cost is the wage times the quantity of labor plus the price of capital times the amount of capital. Okay, can we say that? Can we say that? Okay. So our production function Q is a function of capital and labor, and that's our cost function. Yay. Yay, 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 yay. So now this is P times Q minus the wage, labor minus, okay, we substitute that in there, and we know that revenue is price times quantity. This is a competitive firm, right? And then we can put that in for there. So let's just assume that this is the simplest possible Cobb-Douglas. The simplest possible Cobb-Douglas is this. Well, it's simpler than that even, because I screwed that up. Just ignore that. Simplest possible Cobb-Douglas, Q equals L to the alpha and K to the beta. Okay? Where we don't put any restrictions on what alpha and beta are. All right? So alpha is kind of marginal productivity of labor, and beta is kind of marginal productivity of capital. Or it's more complex than that, but just think about it that way. Okay? That means I can say P times L to the alpha times K to the beta minus, yeah, I know I'm screwing that up, minus that is my profit function. Okay? Now I can maximize that, right? Yes? I can find two partials. I can find the partial of my profit with respect to labor and the partial of profit with respect to capital. Now I'm looking at what effect changing amount of labor I have does to my profits, and I'm looking at what effect the amount of capital I have does to my profits. Okay? And that's going to be P alpha labor, alpha minus 1 K to the beta minus W equals 0. Okay? Yes? So, yeah. And this is going to be P L to the alpha beta K to the beta minus 1 minus R equals 0. It's exciting. Okay. Now we could go through and do, create a Hessian and do all that stuff, but we're not gonna. What this tells us is what? So the more labor I have, the less value there is in adding labor to increasing my profits, and the more relative value there is to adding capital. And I could figure out the ratio of those. I could deal with, capital labor ratios, and we can find the optimal amount of labor, okay? And the higher the wage, the less value there is in me adding labor, okay? And just the opposite here. So I can, for example, figure out that there's some optimal amount of labor, and that optimal amount of labor turns out to be this. Yeah. W to the alpha minus 1 times R. And I'm messing this up, but you don't have to worry about it. Okay, beta minus 1 equals, and that's squared. Okay, more or less. And I might have screwed that up, but let's go with the flow. So what do we tell us? What does it tell us? Well, Well. When wages are high, the optimal amount of labor is low. When the cost of capital is high, the optimal amount of labor is high. There's this relationship. We already saw it up here, right? If I have a lot of labor, the optimal way to increase profits is to add capital, not to add labor. If I have a lot of capital, labor is more effective. If I have a lot of... There's all kinds of stories I can tell. Now, again, you're saying, why did I show you this? Well, let's think about this for a second. Because really what we're doing when we do this, and we could write out all the parts, right? P times Q minus, yeah. Really, what are we doing? We're maximizing revenue subject, that's the word subject. I can't write. You should be, well, if we had this in class, I get the same way. By the end of the semester, when we've been going every day over and over and over again, and we're doing all this stuff, I get more and more error prone by the end, and you guys get way better at yelling at me for making errors, and so we have a much more, by this time in the summer, this should be a highly interactive experience where we're going back and forth and you're pointing out my errors, and yeah, I'm thrilled by that. Subject to, right, a limit on how much my limit, and I don't mean math limit, on how much labor and capital I can afford. Okay? So there's a cost to private labor and capital. What I'm really doing is maximizing my revenue, but subject to trying to control my costs. Okay? Yeah. I can tell you're excited by that. So excited.